Let's talk about 7.2, the central limit theorem with the means. So in the last section, we actually learned about the central limit theorem and what it actually was. So now we're actually going to use the properties of the central limit theorem to actually estimate the means and standard deviations of a sampling population, as well as use it to calculate some probabilities for the sample means. So understand that if you are going to be using your tables, you're going to need to be able to put everything in a standard score. But when we look at standard scores for a sample mean, according to the central limit theorem, either it was originally normally distributed to begin with, or there's a sample size of at least 30, then we actually have to take that into account when looking at our standard deviation, because our standard deviation is a little bit different. So that actually changes the formula up just a little bit, not by much. So if you remember when I told you earlier on in previous sections, the best way to memorize this formula for a z-score is always your data value minus your mean divided by your standard deviation. Our standard deviation for this one will change because I'm referring it to the sample means itself. So since I am referring to a sample mean, not a data point in general of like an individual one, then we have to use this formula here, which is basically our standard deviation divided by our square root of n. And again, this is a population standard deviation. Now, I did make note here that this is the population mean here. And remind yourself, if the central limit theorem applies, it's actually the same for the sample means. Okay. And again, just in case you need to know what all those symbols again, remember X bar, that is actually referring to the sample mean itself. This is basically when we refer to it in this problem as the data value itself, because we're going to be asking about some of them as data values. But I do want you to kind of read the problems and see the difference between them. So we're going to look at one where we can kind of see that slight difference in the question. So according to the Central for Disease Control and Prevention, so the CDC, the mean total cholesterol level for a person 20 years of age and older in the US from 2007 to 2010 was 197 mg divided by DL. Okay, now basically, I'm going to ask you, what is the probability that a randomly selected adult from that population will have a total cholesterol level of less than 183? And we're going to use a standard deviation of 35 and assume that the cholesterol levels for any population are normally distributed. Now, what you kind of need to make note of, and this is the part that I really want to bring attention to, is it says, what is the probability? So we already know that we're doing a probability problem. But what's really more important than that, what is the probability, is actually the next part of it. So in that next part, it says that a randomly selected adult from the population. Okay, that's really important, and remember that. So keep that in mind because that's going to change how we do the problem. And then the next part is, so basically we're looking for what is the probability that basically our randomly selected adult is less than 183. Now they told me in my problem already here is our mean or our average, okay? They gave us our standard deviation. So let's basically put this into a picture. Let's actually sketch it since they said it's normally distributed. So we're going to begin by sketching that curve, and it's normally distributed. There's that 183, and I said the word less in it, so that's going to be everything this direction that I want to know. Okay, and we know that 183 is actually smaller than our actual mean there, so I did put it on the left side here. So if our answer is bigger than 50% or 0.5, then I've done something wrong. Okay, now the second part that I said, and I brought your attention to it, but I really kind of need to really make your attention a bit further here, is we actually are going to have to either do two things. So you're either going to use your calculator or the tables. Now I'm going to show this one with the tables, and then after this I'm not going to show the tables. But the biggest part that we actually have to worry about is that 183, is that it's important to note that in the first part of this problem, we're actually referring to an individual and not a sample. So remind yourself that as you are looking at this one, and let's go back and look at that problem in particular. Notice there that the words say that a randomly selected individual, and that's the part where I kind of wanted to throw into your attention there. A randomly selected adult from the population. I'm not asking about a random selected sample. I'm not even giving you what n is. I don't have a sample size or anything. I'm literally talking about a randomly person, one person in from this entire population that I'm looking at here. So in this case here, this is why if you are going to do your table method, our z-scores is going to be slightly different. So because we're referring to an individual and not an actual sample, the z-score formula will just be x minus the mean over the population standard deviation, okay? Which is going to be 183 minus 197 divided by 35, which is going to give us approximately a negative 0.4. It should be negative because we are to the left of the actual mean, okay? And then using the normal distribution tables or the appropriate technology, if you're using the table, we're going to find the area to the left there. So we're going to look up on our table our negative 0.4, and everything to the left of that will be a 0.3346. So therefore, the probability of one randomly selected adult will be that. Now, there is an alternative method, which is that calculator. And again, remind yourself with the calculator there, basically you're finding the area under the curve that was to the left of that 183, so we can still just use that second VARS normal CDF, and then our lower bound there is a negative infinity. Our upper bound was 183. Our mean is 197, and our standard deviation is 35. This is going to give us approximately 0.3446. Okay, so and that's all there is to it. Again, you can use the tables. It's your choice on that. I'm not going to show the tables, but do understand that this is a calculator. There's really not a lot of extra work if you use the calculator method. Now, let's take that problem and take it another step further. So what is the probability that a random selected sample of 150 adults from the population will have a mean total cholesterol level less than 183? Now, again, for this problem here, it's going to really help if we do a sketch of the normal curve. But I really want to point out some key words here that might help us out. It does say what is the probability, so we're looking for a probability, but it's a random selected sample of 150 adults from the population, and that will be less than 183. Okay? So we're taking, instead of an individual, instead of a randomly selected adult from the population, I'm asking for what will be that random selected sample of 150 adults from the population. We'll have a mean, so we'll have that average that's less than 183. Okay, and that changes our problem a little bit. Okay, so again, we're going to sketch the graph. Again, keep that sketch there. It's really going to help. And again, with that sketch, it's just kind of, you don't have to be super amazing, awesome drawer. Like, just kind of get the base ideas there. Okay, we've got our 197 is here, our 183 would be about here, and again, I'm still doing less in it. What I need to make note of is basically what it is actually referring to. Am I referring to an individual, or am I referring to an actual sample? Okay, so if you are using your table, again, this time we would actually have to convert, but our table format this time, the z-score formula is the different formula because we have to apply the central limit theorem. And this time my z-score would be that x bar minus the mean divided by our sample's standard deviation, our sample mean standard deviation, which is that population standard deviation divided by the square root of n. Okay, so on this one here, we're going to have basically our 183 minus 197 all divided by our 35 divided by the square root of 150. This will give us, like I said, it's a slightly different thing because we're talking about will the average of the samples be less than 183? And using our table, you'll kind of notice that pretty much you're going to be told that the table is going to be 0, 0, which is going to say that's pretty much probably unlikely that a randomly selected sample of 150 adults will have an average or a mean less than 183. So it's pretty much unlikely. It's not impossible though. Understand it's not impossible even though I have a 0%. It's approximately, okay? Note how much more likely it is to have a random person to actually have a cholesterol that was less than 183 versus a sample of 150 adults that have an average that is at low. Now, if you're going to do this one in the calculator, again, the same process is going to actually happen. So you can use a table or you can still use a calculator. So with the calculator, again, one of my best things to do is draw the picture. Guys, I really just kind of make note of that picture and get that on there. So again, you know that that mean was 197. We know that we were looking for 183. We know we're going less than it, which is all this area here. That means I have my negative infinity here and positive infinities over here, but I don't really care about it. And then we were told, okay, we were told the mean was 197, but we were told the population standard deviation was 35. They also told us that we had a sample size of 150. And we are basically looking for the probability that our sample mean is going to be less than 183. So because I'm looking for this part right here, which is that X bar, not an X, just an X bar, when I use my calculator, and so let's pull up on the calculator. Okay, so since we're looking for X bar here, it's still that second vars and number 2 for that normal CDF, but here I'm going to have my negative infinity, so I'm going to say -1, and that, don't forget, is second comma to get our EE in there, 99, so there's my negative infinity. My next lower bound is going to be 183. My mean, now the central limit theorem does apply here, and how do I know it applies? Well, basically because our n size is 150, so that meets the minimum requirement of 130 or more. Or it said that it was actually normally distributed to begin with, so it didn't actually matter there either. So, but because the central limit theorem applies, whatever the population standard population mean is, that is actually going to be what we say is the sample means. We're going to use the same thing here. But for my standard deviation here, I'm going to type in 35 divided by, and then the square root of 150. For those of y'all that have this here, guys, notice I'm just typing it in as that actual division. It will help you out tremendously there. And same thing for those of y'all that have a TI-83 that have to put that lower bound, comma, upper bound, comma, and mean, comma, standard deviation. Same rules are still applying. You can actually just type it in with that square root symbol there. You do get this answer that is actually really, really small. And when you look at this, because it's so small, understand that that does round to 0, but let's make sure that we can make that translation the way it actually looks, okay? So in this problem in particular, once you've typed it all in the calculator there, it ends up being approximately 0.000000, and then it's 48, which will round to that 5 there. And that's how I know when I start rounding to the 4 decimal places here, I'm rounding to this decimal, that is still going to keep it 0. But when I say that it is kind of very, very small, it is very, very small. But it is a little bit more accurate to use the calculator than it is to use the table. Okay, so let's try another problem. Again, the biggest part about these is you're going to have a lot more word problems, and you just kind of want to read for some keywords to help us out here. Okay, so elevators are required to have a weight capacity that's posted. Now, if the weights of U.S. men are normally distributed with a mean of 194.7 pounds and a standard deviation of 32 pounds, what is the probability that a random group of 10 men who enter on an elevator will have a combined weight greater than the weight capacity of 2,000 pounds. Now, that is in that elevator in particular. Okay. Again, let's begin by noting kind of one thing is, well, first of all, they gave a sample size, right? Now, the sample size is only 10. However, the central limit theorem can still be applied because it said in the problem that this was actually normally distributed. Okay? Now, the second part that I found that was a little interesting in this problem is as I begin to read it, it says, what is the probability that a random group of 10 men, so they've already given me a sample size, so that kind of lets me know I'm kind of going into my X bar world here, who entered an elevator have a combined weight greater than the capacity of 2,000 pounds. Okay. Now, this problem is worded differently than the previous problems, and the biggest note is that it said the word combined weight instead of a mean. So basically, as we were working on some of the previous problems, everything was based on just a generalized mean. So for this one here, what we need to do is we kind of need to reword the problem is basically say, what is the probability that a random group of men have a mean weight, so an average weight, greater than some amount, okay? And again, it said we are interested in the combined total weight being more than 2,000 pounds, right? But if you take 2,000 divided by 10, that means their average or their mean would be 200. So we can kind of reconstruct that problem. And then from there, we can now draw it. So we know that we've got our 194.7 is in the middle there. That's our mean. We know 200 was that kind of average that we're looking at and saying, well, what's the likelihood that our average is actually going to be more than it? Okay. Now, with that being said, that is all the area to the right. So again, kind of use your appropriate technology here. Whatever you feel like using. If you want to use your calculator, if you want to use your tables, either method will work, but you're going to get kind of a similar answer. Now, the calculator is going to be more accurate. But let's actually plug it in the calculator and see what we get here, okay? So when you're using your calculator on this one, again, I know I've got the answers already approximately 30.02% up on the screen. However, understand that what we're doing is that we kind of drew the picture to help us out, but it also gives us a good idea that we're going to be doing this normal CDF. Our lower bound was 200. Our upper bound there was going to be a positive infinity. So guys, do remember that that's 1 second comma to get that EE part in there. 99, don't just put a regular E in. Our mean in this case was 194.7 and our standard deviation was 32. But remember, I'm asking you in terms of that sample mean. So that's going to be 32 divided by the square root of 10 because we're dealing with the samples standard deviation. So the average of the sample standard deviation, paste it in, and there we get our answer, which is that 30.02% or also 0.3002. Okay, let's try for another one. And again, the more times you do this, the more you're going to kind of start to see the wording change. And this is where I highly recommend just kind of play with the words over and over again. So suppose that the prices of women's athletic shoes have a mean of 75.15 cents, so $75.15, and a standard deviation of 17.89, which is $17.89. What is the probability that the mean price of the random sample of 50 pairs of women's athletic shoes will differ from the population by less than $5? Okay. what is the probability? So we know we're looking for a probability here that the mean price, that the average price of a random sample of 50 pairs. Right away, again, I'm kind of pointing out these words here because these are really important words. And this basically, this is what's telling me right here, okay? That is what's telling me that we're looking for the probability that X bar, okay? So we're going to be using X bar, so that means you're going to be using your standard deviation divided by your square root of n for your standard deviation of that X bar itself, okay? And again, this is kind of like I'm learning this by the word problems that they say itself. Now, the other part that I kind of want to make note of as I'm looking at this is not only that it's the probability of the mean price, and then they give me like the amount there. The best part here is that also will differ from the population mean by less than $5. Okay. Now, what this means is by subtracting 5 and adding 5 to the mean, that's what we mean by differ. That's where we're going to get that above and below option on it. So remember that the mean price they told us up there was $75.15. So I'm going to basically add and subtract $5 from that. And I'm asking for what is the mean price that it will differ, meaning it's going to be between $5 above or below. So what is basically when I draw that out, it's going to look like a normal curve where we've drawn that the mean price is in the middle. Again, I am asking about the word mean price, so this does mean that you're using that standard deviation of the population, standard deviation divided by the square root of n. Do note that, again, I can actually use the central limit theorem here, again, because they either say that, one, it's normally distributed, or your n is big enough. So in our case here, in our one-step calculator method here, is I'm going to put in my lower bound, my upper bound. I'm going to put in my standard deviation and my population's mean, okay? And again, it's always in the same format. So lower bound, upper bound, my mean, and then my standard deviation. And guys, don't worry about it. You can literally just put in that $17.89 divided by the square root of 50, okay? For those of y'all that have a TI-83 calculator, it's going to look exactly like this. Please be sure to close the parentheses on that square root symbol. If you have a TI-84, just make sure to either arrow out of the square root symbol or close the parentheses on it, depending on how you have it set up. So pretty much the way our answer works here is that even with the calculator, you can still find the exact same answer with the table. Is the probability of a random sample of 50 pairs of women's athletic shoes having a mean price or an average price that differs from the population mean by less than $5 is going to be a 0.9519. So it's pretty much likely to happen. Let's try another problem. So at a local manufacturing plant, the screws being manufactured have a mean length of 1.625 inches with a standard deviation of 0.01 inches. Now, the quality controller randomly chooses a batch of 50 screws. What is the probability that their mean length differ from the mean of the population by more than 0.004 inches? Now, this one's a little bit different. Very similar to the last one we did, but just slightly different. So again, if the quality controller randomly chooses a batch of 50 screws, so we're even told that we have like 50 screws, so we have an n there. What is the probability that the mean length differ from the mean by more than? Okay. Now, differ is going to allow us to basically add and subtract. So that's the first thing I note there. Okay, so basically I'm just adding or subtracting. However, the next part is that I said differ by more than. So when I talk about differ by more than, I'm literally talking about the outer part of the tails here. Okay, so I'm still going to take that mean of 1.625 and I'm going to add and subtract 0.004, which is going to give me the 1.621 and the 1.629. And again, I want to know the area here out in this tail area and here because I said more than. Now, because we want to find the total area in the two tails here, we're actually going to use the complement rule for probability. And the reason why I say we're using the complement rule is I'm going to scroll back to the picture one more time. I don't really have a lower bound because if you think about this in the way that we're looking here, is I'm looking for the area that is actually covered between here and here. Okay, so since I'm actually looking for this area, that's got a negative infinity, so I would have this is my lower bound and this would be my upper bound. And then I'd have to do the same thing here because I'm looking for this area here, which that would be the lower bound. And then my upper bound here would be a positive infinity, right? So this would involve me doing this twice. So I'd have to find the area under the curve, also known as the probability of here and then add them together. Or, well, this is where that complement rule comes in. What if I find the area here and then just subtract from 1 because that's going to be the opposite or that complement? Okay, and so that's pretty much what I would suggest to do is using that complement rule, find the area between the two items and then subtract it from 1. Okay, so use that appropriate technology there. In order to do this, do understand that you're still going to get an answer, but it is a little small, but it makes sense because we're dealing with screws, so like we don't want our probability to be that off. But when you do this one step in the calculator, be sure to start with the 1 minus, as I show here in that first screen on the calculator. And then once you've got 1 minus in that home screen itself, okay, once you've got it here, then you're going to hit second vars and go to the second step here and get your lower bound, your upper bound, your mean, and your standard deviation. And again, this one is a standard deviation of a sample. Okay, and then paste it in. And as long as you've got the 1 minus before you hit the second vars here, you'll notice it will show 1 minus and then normal CDF. And that will be one step to get your answer, which is going to be a 0.0047. And that's all we need.